So fluid dynamics is the flow of fluids, and in the diagram you have three that are flowing inside the human bodies. Of course, blood is flowing, isn't it, through the aorta, which is the main artery, and then it branches out into capillaries. You know that. We all have blood flowing through our bodies. And then you have water flowing there as the firemen are trying to fight the fire. Water is flowing, and then smoke is flowing. Is smoke also fluid? Yes, because a fluid means a liquid or gas. Later on in the chapter we'll see that there are two types of flow. One is called a laminar flow. The other is called a turbulent flow. We'll come to that. Smooth flow and irregular flow. We'll come to that later on. Now we begin with a formula there. You consider a small cylindrical column of a liquid flowing, like a liquid flowing through a tube, and that tube will have an area of cross section, right? Area of cross section, which would be pi r squared, because it's circular. And if you consider that in t seconds, let's say that in t seconds it flows from this point right there to this point in t seconds. So isn't this the cylindrical column that has been flowing in t seconds? How do you find the volume of that cylinder? How do you find the volume of a cylinder? Area times the length, which is d in this case. So A times d will give you the volume. And if you divide it by time, what do you get? You will get the volume flowing in 1 second. And that is represented by Q. So whenever you see Q, you should know it is the rate of flow. Q is the rate of flow. It's good to write down because you'll have about 6 formulas today. Q is the rate of flow, which means the volume flowing in 1 second. The volume flowing in 1 second. Okay, take a look at this. So you have A times d by t. What is d by t called? D by t. Velocity. Let's call it the average velocity, because the velocity may be a little different, at different points. So now you have a formula here. To find the rate of flow, all you got to do is multiply the area with what? Velocity. Area times the velocity gives you the quantity. Q stands for quantity, rate of flow. What's the unit of rate of flow? Unit. Come on. Meter cube per second. Meter cube per second. So you can write that down. Q is measured in meter cube per second. That is your formula number 1. So I'm saying rate of flow, Q is just interesting fact that 5 liters of blood flow in a minute in the human body. Did you know that? 5 liters in 1 minute. That is the rate of flow of blood. See, most students make a mistake about confusing between these two terms. That's why I had to write Q and average velocity are related, but they are different. Okay, what's the difference between them? What's Q? Rate of flow, measured in meter cube per second, right? And what's V there? That's the average velocity. So they are proportional, because if one is bigger, the other one is also bigger, naturally. If the velocity is high, then the rate of flow is high, but they are not the same. That's what I'm trying to say. They are not the same. Okay. Now take a look at this tube. It has 2 different cross sections, a bigger part and a smaller part, and without telling you anything, just mere intelligence, tell me where would the liquid be flowing faster? In the smaller tube. Correct? Definitely. Why? What's the reason? put some logic into it. What you said is correct. It will be flowing faster through the narrow tube. But why? Don't bring in pressure. Just idea. Therefore, that's because the fluid does not get collected as it flows. Does it get collected? So whatever comes in must go out. If whatever comes in must go out, then being smaller, it should flow faster. Common sense. That makes sense? Okay. This is called the equation of continuity. The equation of continuity means continuous flowing. That's what it means. Whatever comes in goes out. All right. What comes in? Q1 is equal to Q2. Q1 is what comes in. Q2 is what flows out. And Q1 would be A1 times V1. Right? And Q2 would be A2 times V2. That is the equation of continuity. Therefore, since A2 is less than A1, V2 would be greater than V1. Isn't it? That's it. That is the equation of continuity. Many times if you're trying to water your plants and the hose doesn't have enough length, what do? Doesn't have enough length, the water doesn't reach one corner of your yard, what do? See, that's exactly what you do. You use your thumb and make the area of cross-section smaller. What happens? As you make it smaller, the velocity becomes higher and it jets out and reaches there, right? Unfortunately, this is the same thing that happens when people take in a lot of cholesterol and plaque builds up within the arteries. You've heard about this, isn't it? We'll do some more calculations that will really open your thinking as we go on. Even a little bit of cholesterol, plaque build up, velocity becomes huge, the blood pressure changes. So, need to be careful. We'll come to that soon. Okay, that was number 2. Bernoullis Principle, 1700s. 18th century at least, it has been there. But did you know that this is the principle used in making an airplane fly? No, you didn't, did you? Okay, you're going to see. You're going to see. This is called Bernoullis Principle. But before you get to the airplane and all that, take a look at this picture and try to understand. Even when I wait at Cunningham on Fairmont Parkway to turn left, as the vehicles pass on Fairmont Parkway, I feel my car shake a bit. Haven't you felt that? It's scary. There's no wind blowing. It's when the vehicles pass. You know why? Look at this diagram. Look at the diagram carefully. Tell me what would be the velocity of airflow here as compared to the velocity on the sides. All right. Higher. Why? Because a part of the air is being carried by this big one, this direction, and a part of the air is being carried by this one in the opposite direction. Let's imagine both are moving in opposite directions. Okay? So now the relative velocity is bigger between the vehicles, isn't it? Because one part is going that way, let's say at 10 meters per second, the other is going at 15 in the opposite direction. The relative velocity is like 25 now. So what I'm saying is this. Between the vehicles, the velocity of flow will be higher. Where the velocity of flow is higher, I'm going to show you that the pressure will be smaller. That's the important part. Where the velocity of flow is higher, the pressure would become smaller. What happens when the pressure is small? Would you have something get sucked into that region where the pressure is smaller? Yeah, everything flows from high pressure to low pressure. So as the vehicles pass, you feel a drag towards them, which is dangerous. It's like one getting sucked towards the other. I know you have not traveled in trains, have you? Have you? Okay. Fast-moving trains on adjacent rail tracks will not be allowed to go in opposite directions. Fast-moving trains moving in opposite directions on adjacent tracks. Now, they won't let you do that because the train is huge, isn't it? And when this pressure difference happens, because it's long, there is a good chance of derailment, if you know what derailment is. So they will always slow down one, or even bring it to a stop and let the other pass. Did you understand what I said? So what do we get from here? Where the velocity is higher, the pressure is lower. Okay. We can actually... So where the velocity is higher, the pressure is smaller. That's what I've been saying like 3 times now. That is what you get out of Bernoullis Principle. But here's the equation coming up. There are 3 terms in Bernoullis equation. You can see, and the sum of all the 3 terms is a constant. The first term is a P.
Okay.
The second and the third, what does rho represent? Density. Okay, like, so there are 3 terms. The first term that you see here is pressure energy. The second is kinetic energy. And the third is potential energy. But you look at it and say, man, wait, what's the formula for kinetic energy? Anybody knows? But why is this like this? It's not mv squared, it's rho v squared. Why? Because it is the kinetic energy of unit volume. Kinetic energy of unit volume. Let me show that to you. Did you say kinetic energy is 1/2 mv squared? Yeah, the last one is potential energy. What happens if you divide this by volume? What is mass by volume? Density. That's how you got 1/2 rho v squared. Okay, that's velocity, this is volume. Don't cancel them out. Mass divided by volume, okay, is density. So this is kinetic energy of 1 meter cube. That's what I mean, because we divided by volume. Kinetic energy of 1 meter cube. Okay, what's the formula for potential energy? mgh. Do the same thing. If you divide by volume, what do you get? Mass by volume is again density, so you get rho gh. So this is potential energy of 1 meter cube. The first term, trying to write it in that order, the first term is actually supposed to be pressure times volume. That is called pressure energy. You may want to write this down because it's new. Pressure energy, because a fluid can exert pressure. So it has pressure energy, which is given by the product of pressure and volume. If you divide that by volume, what do you get? Just pressure. Okay. So how do you state Bernoullis principle or Bernoullis equation? Simply, the total energy in a flowing fluid is a constant. The total energy in a flowing fluid is a constant. What do you mean by that? That means if you take any 2 points where the fluid flows, you take the total energy at one point, take the total energy at the second point, how should they compare? They will be equal. So just like you do in chemistry, we can write it as, look, P1 plus half rho V1 squared plus rho G H1 is equal to P2 plus, help me out, half rho V2 squared plus rho G H2, they should be equal. Haven't you used the equation like P1 V1 is equal to P2 V2? That's what I'm talking about. When you say it's a constant, at any 2 points, they must be equal. Okay. So that is kinetic energy per unit volume, the second term. The third term is potential energy per unit volume. And the first term is pressure energy for unit volume. Okay, and I also mentioned if H1 is equal to H2, that means the tube is horizontal. then you only have to consider two terms because the potential energy term gets cancelled. And whenever you're asked to do problems, you will only have to do this. So for you in all problems, potential energy will be the same. That is the equation that you have to know. Because there. Have you looked at the shape of the wings of an airplane? How's the top part? Curved. And the bottom part is flat. Right? So the view that you're getting here is, what kind of view? The airplane is like that? Is it like this? No, it's like this. You're getting a lateral view like that. So you're seeing the top part and the bottom. And as the airplane picks up speed, come on, air begins to flow. One part flows over the top, the other part flows over the bottom. And because the top part is a little bit bigger, being curved, the air has to flow faster. Come on. Because whatever mass of air divided at this point, whatever divided here, they should meet together here. Equation of continuity. And isn't this part bigger? So the airflow will be faster here, isn't it? Where the flow is faster, what happens to the pressure? Decreases. So the airplane gets sucked up. So the faster it moves, the lesser the pressure on top of the wings, so it gets. That's the only reason why the airplane is able to stay there against gravity. It's scary if you think about it. That's the only reason. If the speed becomes zero, it's only as long as the airplane moves. And when you go higher, what happens to the density of air? Decreases. So that means it has to keep moving very fast in order to have that pressure differential. You know what I'm talking about, right? It has to move very fast there. And we have a problem to do on that. The second figure, B, shows a sailboat. Do you know what it is? Isn't it the same principle? Look at it and understand. You can see. Where the streamlines, these are called streamlines. You see the streamlines here are crowded. Aren't they crowded here? That means it's faster. So the pressure becomes low and the sailboat gets sucked. You can see here. Pressure here is less. The pressure here is bigger. So it gets pushed in that direction. If you have a huge sailboat, you're going to get a big force and it keeps moving. That's how they discovered continents. Just believe that. Is that true? Yeah, and they were not lazy people. None of these people were lazy. Not right, brothers. They had no exam to take. Aren't we happy that somebody did that without listening to music the whole day and watching TV? Yeah, I mean, just think about it. That we can fly across from here to India, the flight is 22 hours. That's the opposite side of the globe. If there were no airplanes, just think about how many days in the ocean. Be glad. So we're trying to follow their path. Lift off the airplane, and I've explained it. If you have any questions, you can ask me all the time. I hope you understand what's going on. That's the sailboat, as I said. All right. Torricelli's theorem. This is an Italian scientist. What you see there is a dam in which you have water collected to a certain height. Come on, try to understand. And as the shutters are opened here, as the shutters are opened, you can see that the height is h from the center. The shutters are open, water flows out. What we're trying to find using Torricelli's theorem is to find the velocity with which water comes out. Did you hear me? With which water comes out. What's that velocity in this diagram? V2. What's H2? Height. Okay, let's say we are trying to measure the height from here. So then what will H2 be? See, you could measure height from anywhere. Let's say you measure height from here. Then this would be the height, isn't it, h2? But what if you measure height from exactly the center? What is h2? 0, correct? Then, in that case, h1, will actually become h. Anybody listening to me? Because if you start measuring height from here, then h1 is equal to h. Okay. What's the velocity on the surface? Why? Because it's a huge dam. And do you see the water level go down like, as you stand there? Does it go down? Jet down? No. It's basically not moving, isn't it? So what's the velocity at top? 0. What's the pressure at the top? What is P1? See, you get so many chances to answer. What is the pressure at the top? Is there any pressure acting? Wait a minute. Is there any pressure at this point?
Yeah.
Thank you. Atmospheric pressure. Okay. What is the pressure just outside the hole there? Just outside. Atmospheric. Did you hear me? So the pressures at the top, P1, and the pressure P2 are equal. Remember, P2 is not the pressure inside the liquid. Because what are we trying to find? We're trying to find the velocity with which the liquid comes out. Therefore, point 2 is a point not inside the liquid, it's just outside the liquid. See that? Just outside. So therefore, what's the pressure there? Atmospheric. So you have atmospheric pressure here, you have atmospheric pressure there. What's the height H2? 0. What's height H1? Okay, so substitute it into Bernoullis equation. Go ahead. I've written a part of it. Go ahead. Come on. Write it and get me the equation. I'm not going to show it to you. Get me the equation. I told you that is Bernoullis equation on top. Then substitute the conditions that I told you. Because Torricelli's theorem is obtained from Bernoullis principle. So that's Bernoullis principle. You already saw one part of it. Isn't P1 equal to P2? Come on. Both atmospheric, so you can cancel those two out. What else did we say? Which velocity? V1 is 0, so put V1 0. And what did we say about H2? Okay. Put all those there in that equation and make V2 the subject. Let's see who will get it. Make V2 the subject. Because we are interested in finding the velocity with which the liquid flows out. Make V2 the subject. Hope somebody will. Okay, P1 is equal to P2 because it's the atmospheric pressure. And then you get this. Let me just run it through fast here. I put it as H1 minus H2 till the end, and then put H2 is equal to 0. Okay? That's the same thing, which makes H1 equal to H. Isn't that what you got? And if you have on top of that, that velocity 1 is 0, then you get what you got. So you're right. You're right. So V1 is 0, you get that. But this is exactly what you would have got. Watch this. If you had dropped an object from the surface, but outside the dam, okay, not inside, not through the water, what would its velocity be when it reaches this point? Wouldn't it be exactly square root 2g h1? What an amazing result. So according to Torricelli's theorem, the velocity with which a liquid flows out is exactly equal to the velocity attained by an object falling freely outside the liquid. That make sense? And how did Torricelli get his theorem? From Bernoullis principle. Just an application of Bernoullis principle. All jobs are good. What can you say about the pressure of the water at the top? Simple pressure. You saw the word. You saw the word. The question doesn't hold any water anymore. What can you say about the pressure? Pressure of water at this point as compared to at this point. Pressure. Let's call this 1 and this 2, where's the pressure higher? 1. Definitely it will be a reduced pressure here, isn't it? As the height increases, the pressure decreases. Reduced pressure. How much will it decrease by? Because as it goes up, it gains potential energy, doesn't it? So it will have to lose kinetic energy. Because the total energy is constant, remember that. So if potential energy goes up, kinetic energy goes. Like if you had kept on increasing the height, wouldn't there be a point where it just does not even come out? Yes. Come on. So just think about a 100-story building and you have to send water to the top floor. Think about how much pressure there should be. Hello? It's not easy. People there on the 100th floor can easily complain. We don't get any water. Yeah, they do because of all the physics. The pressure has to be so high so that it reaches the 100th floor. There you go. All right. Laminar flow. There are 2 types of flow. Laminar flow and turbulent flow. And one example will prove it in a minute, the difference. Take a look at this. All right, that's all. That's all you need. At the bottom, you see the smoke coming out? You see at the bottom that it flows smoothly, right? It's a smooth flow. That is laminar flow. What about at the top here? As it mixes with the air. Is that a smooth flow? No, that is turbulent flow. That's it. So laminar flow is a smooth flow. Where you have it flowing here, right here. Smooth flow. But as it comes up and reaches here, that is turbulence. You know, before they put vehicles on the road, they test it. Oh, I'm sure you know that. In wind tunnels. You know, what's a wind tunnel? They make a prototype. Yeah. And they're checking for so many things, but mainly they're checking for turbulence behind the vehicle. As it cuts through the air, you do not want air behind creating a turbulence. Why? That'll create a pressure difference and lose a stability. So they have to check that. And when I think of laminar flow, I think about fishes cutting through water. Have you seen the shape of a fish? Yeah. And as it cuts through water, does it disturb the water? Nope. You don't see it disturbing the water because that's laminar flow. And we've taken a clue from nature. We've tried to shape everything according to the shape of a fish. Yes, that's what we've done. Look at the sports cars. Aren't they almost shaped like a fish? Yeah, look at the front. And when we send rockets up, we make it even more pointed, so the flow is laminar, the flow of air. No turbulence, no friction. That's what we try. All right. One of the last formulas is called Pushel's formula. That's a French scientist, so you have to read it as Pushel. Pushel's law. I just want to finish the topics and then do problems. So this last one, maybe 1 or 2 more, maybe. I just wanted to finish it. Pushel's law. This is not Pushel's law that you see here, but please listen. Towards the end is when people get sleepy. So these are the layers of a liquid. Imagine that the liquid is divided into so many layers. Are you listening? Don't lose it. This layer is touching a solid. See that? Therefore, practically it's not moving because of the cohesive force. Have you heard of those terms called adhesive and cohesive? Adhesion is a force between 2 different molecules, and cohesion is between molecules of the same kind. So here you're going to have adhesion, isn't it? Adhesive force between water and glass, for example, water and glass. Adhesive force. That's called an adhesive force. You could call it friction. Because of that, practically the liquid is not moving. But as you go to the top layers, the velocity keeps increasing. You see that? Therefore, there's a velocity differential between the layers. So let's say you take these 2 layers in green. Wouldn't there be a difference in velocity between those 2 layers? There would be. And therefore, just imagine 2 people trying to run, holding their hands. One wants to go slow, the other wants to go fast. Wouldn't there be an internal force between them? But what if both were trying to run at the same speed? Then there would be no force between them. That makes sense? One is trying to run at 9, the other is trying to run at 10. Surely one is trying to slow the other one, the other one is trying to speed up the other. So there's a force between them. Same thing happens in a liquid because one is moving at slow speeds and the other is moving at a faster speed and they are touching each other. Just take these two layers. Don't they have a difference in speeds? And they are touching each other, so there is an internal friction. And the internal friction force is given by this formula. Internal force between liquid layers is given by this formula. Okay, understand the terms. What is F? Friction force between the two liquid layers. Okay, you find a constant, it's not N, it's eta. It's an N with a tail. Longer one, this should have been longer, eta. It's called the coefficient of viscosity. The coefficient of viscosity. Somebody tell me, what is this? Velocity. Actually, it's a velocity difference. Velocity difference, here it's velocity because we already took this to be 0, that's why. So please write this as velocity difference. Did you do that? Velocity difference. What's a area? Area where they are touching each other. So that is the area of contact. So instead of holding hands, if two people run embracing each other, that's going to be terrible. More area of contact, more friction. Okay, what's this? Distance between the two layers. Look at the diagram. Isn't that the distance between the two layers? Come on. So if it is adjacent layers, somebody answer this question. If it is adjacent layers, what's happening to the length now? Smaller or bigger? Smaller. Therefore, what will happen to the force? If the denominator gets smaller, the force gets bigger. Yeah. Okay, so when you rearrange, this is what you get. That is the coefficient of viscosity, its unit. If you give the units of force, length, velocity, and area, you're going to end up with Newton per meter squared times second. But Newton per meter squared is called Pascal, so the unit is Pascal second. It's not it's Pascal second. That is the unit of coefficient of viscosity. What does this mean? This is where we compare liquids. Come on. Have you ever tried to buy motor oil? Don't you have different grades? Yes. They say 20W40. You have never heard about it? 2040, 2030. It's the coefficient of viscosity they're talking about. Depending on the vehicle, you have, if it's a smaller one, you have less viscosity one. Come on. And what happens with temperature? What happens to the viscosity of a liquid as you heat it? It thins down, which means the viscosity goes lower. Yeah, simple questions like why is hot soup, basically why are hot foods tastier than cold ones? You never thought you would hear this in a physics class. Now ask this question to a biology professor. Normally they will not answer. I'm not trying to ridicule them. I don't know so many things either. But especially liquids, when cold, they don't taste. Think about cold soup. Would you like to take cold soup? Okay, hot soup is tasty, isn't it? Definitely you got to tell me why. Go on. Why is hot soup tastier than cold? Okay, what happens to the viscosity of hot soup? Smaller or bigger? Smaller. Therefore, when you put it on your tongue, it spreads easily, touches every taste bud. It's tasty. Cold, rolls up. It doesn't touch the taste buds. I don't like it. That's it. That's why hot soup is tastier than cold. Don't look at me like that. Just told you. Okay, I could ask you that question. This is Pushelse law. I'll let it roll down, then I'll tell you what the terms stand for. This is one of the biggest formulas that you will ever study. Okay, look at the left-hand side. What's Q? What does Q stand for? Quantity of flow, which means volume flowing out in 1 second, isn't it? Okay. P2 and P1, if you look at the diagram, you know. Just tell me. Looking at this diagram, where is the pressure higher? P2 or P1? Where is the pressure bigger? P2. How do you know? Because the liquid is flowing this way, isn't it? So P2 minus P1 is the difference in pressure. P2 minus P1 is the difference in pressure. Okay, what's R? Radius of the tube. Radius of the tube. Okay, what is eta? The coefficient of viscosity, or simply call it viscosity. And what is this? The length. Oh yeah, that looks funny. Anyway, that's the length. Yeah, it looks like. Don't make fun of me. Come on. Okay, so Q is the volume of liquid flowing out in 1 second. It depends on all these terms. What? That's an 8. Yeah, that's an 8. Oh, what does it look like? Yeah, 8. Yeah. 2 and what does it look like? Oh, you couldn't believe that there's a number in a formula, right? Okay. Yeah. What? Q is volume flowing out in 1 second. There are several terms on which volume flowing out depends. Which term does it depend most on? Which term does it depend most on? Oh, come on. There are several terms on the right side. On the radius. Why? What do you see? Radius raised to? That's the problem. When the arteries get clogged up, that is the problem. Listen to me. If the radius doubles, or no, wait. If the radius becomes half, when it gets clogged up, of course the radius decreases, isn't it? When the radius becomes half, do you know how much this will decrease? 16 times. 2 raised to 4 is 16. 2 times 2 times 2 times 2, 16, isn't it? So if the radius of an artery just becomes half of what it was, that person is dead. Because now the flow velocity is what? 16 times less. Therefore, the heart has to pump even harder to make the blood flow. Are you getting what I'm saying? Yeah. Therefore, even a small decrease in radius of the arteries is very dangerous for human beings. That is because of Pushelse formula. And that's why you had to learn this. Because it's very important for you to know, to tell your patients or whoever you're dealing with, have some exercise. Don't eat food, fast food, cook some food. Save money and save your life. Don't be lazy. I'm recording. How high are raindrops coming from? Very high, isn't it? If it was accelerating at 9.8 meter per second squared all the way down, what do you think the velocity would have been by the time it hit your head? Really big, and the momentum would have been high, because momentum is the product of mass and velocity, isn't it? That it would have felt like steel balls hitting your head. And you would have had to carry steel umbrellas. Why? Because otherwise people would have died. Newspaper reports, people died in the rain. Never happens. Why? Because as it flows, it's cutting through the air, and the viscosity of air, are you listening to me? The viscosity of air is slowing it down. We call it air friction, whatever. And so after a little bit of movement, it attains a constant velocity. It's called the terminal velocity. When does that happen? If the gravitational force is balanced by the viscous force. What's the net force then? What's the net force?
0.
And if the net force is 0, what's the acceleration?
0.
Therefore, the velocity will stay the same all the way till the bottom. Did you get it? So, in the beginning, the velocity is 0. It accelerates for some time, right? As it picks up speed, the air friction is also increasing, and at one stage, both become equal. mg down, air friction up, both equal. Beyond that stage, it's not going to accelerate. That is called the terminal velocity. And when it attains the terminal velocity, the formula for force acting on that raindrop is given by Stokes Formula. Stokes Formula gives you the force acting on the raindrop or any object falling through a viscous medium. This is the formula, 6 pi eta RV. Okay. Let's explain the terms. Well, 6, you know, for a long time you've been saying 6. Pi is a constant, you know that. What's that? Viscosity, coefficient of viscosity of what in this case? Air. What's that? The radius of the raindrop. The radius of the raindrop. So if it's big raindrops, they're going to have a bigger force acting. That's what it means, isn't it? And what's this? Terminal velocity or velocity. This is called Stokes Formula. That brings us to the end of the theory in this chapter.